The section 4.1 chain rule. The chain rule is a rule that we use on derivatives of composite functions. So I was saying, up until now, when we had something like 2x minus 4 to the fifth, what would we have to do? Multiply it all out, and then take the derivative of the expanded polynomial. Well, 2x minus 4 to the fifth would be a pain to multiply it all out. And when we get into trig functions, it gets a little trickier. There's nothing we can do to multiply it out sometimes. So we need to have some method that we can use to take the derivative of these composite functions. And the way that we will do this is we need to consider an outside function and an inside function. And now sometimes there's more than one inside function, but we need to get good at spotting what is the outside thing going on and what is the inside thing going on. So if we look at 2x minus 4 to the fifth, well, the inside of this one is easier to spot, I think. And the way we're going to write this, the outside function, we're just going to say is something to the what power? To the fifth. Something to the fifth is what's going on the outside. What's going on the inside, now you don't ever choose to separate things that are added or subtracted. The whole inside is 2x minus 4. Okay? So with composite functions, we have to be good at knowing where to begin, and to do that, we have to recognize outside from inside. All right, the second one we have here is sine squared of 3x plus 2. My best suggestion for this, anytime we see sine squared, we rewrite it as the sine of 3x plus 2 all squared. That makes it far easier to tell what the most outside function is, which would be what? Something squared. So our outside function is something squared. And then we want to move to the inside. Now this one gets a little trickier. So I'm going to underline what we have for the inside, which is all of that. But we notice that that is also a composition, isn't it? What's the outside of this composition? Sine x. So our next one, moving inward, would be sine of something. And then finally, the furthest inside would be what? 3x plus 2. Okay, our next one, secant of x squared, the outside function is secant of something. And the inside is x squared. All right, so on this final one, I want you to label that y equals 2 times the quantity 3x plus 5. And we're going to use a little notation here that leads us to the formal form of chain rule. And to do that, we're going to say, well, okay, let's let the inside equal u. Let u equal 3x plus 5. So now our outside function, if we write it in terms of u, we would have y equals 2 what? 2u. And then our inside function would be u equals 3x plus 5. Okay? So the reason it's helpful to think of it this way is because it leads us to this formal idea of the chain rule, which is, and I should make that a little larger, to the back. Chain rule is used for composition functions. And if we are looking for dy dx, which means the derivative of y when the variable is x, then we can do dy du times du dx. Well, what happens when I multiply dy du times du dx? The du's cancel, and we are left with dy dx. So if we could find a way to write our derivative in terms of u, then we can take the derivative of y with respect to u, which means the variable of u, and then we can multiply by the derivative of u with respect to x. So let's see what that does for us over here on the final problem that we have. Move this a little lower. So if I want to find dy dx equals, what is dy du? Well, here is y equals 2u. So that means take the derivative of y with your variable being u. So what is that? That is just 2. Times the derivative of u with your variable being x. So what would that be? 3. So this is dy du times du dx, and we get 6. And if we were to have taken the derivative the way that we knew how before today, we would have had 2 times 3, or 6 as well. So you will never force the chain rule. It's just that it's very easy to see with this simple problem. Okay, I would never force you to use chain rule to solve that derivative. But there are others where you will need to use it. All right, this form that you see here becomes very important. Put stars around it, see what you need to do. There are many problems that we run into later when we end up solving for something. And if you can determine this little chain, it will help you solve the what's missing. Okay? And then over on the right, I have the way that I think about chain rule every time I do it. Derivative of the outside, leaving the inside alone, times the derivative of the inside. And you'll hear me say that a million times. Take the derivative of the outside, leaving the inside alone, multiply by the derivative of the inside. We have just shown that this chain rule, this dy du times du dx, does give us exactly the derivative that we would have gotten had we distributed the 2 through. All right, so let's go see some more examples. May I move? I'm going to go ahead. All right. Also here, you don't need to write all of this. I'll read through it and I'll highlight the important parts. The chain rule, if f is differentiable at the point u equals g of x, and g is differentiable at x, then the composition function, remember fog, f of g of x, which can also be written f of g of x this way, is differentiable at x. So this is the other way that you'll see chain rule written in function notation. So this is what I want you to be comfortable with. The derivative of f of g of x is equal to, the way we write it is f of g prime of x. I tend not to use the open circle notation. I use the common composite notation, f of g of x, like this. And take a look what we have here, f prime of g of x. Well, that is the derivative of the outside, leaving the inside alone, times g prime, which is the derivative of the inside. And then the way that we saw it on the other screen, right. So this is using function notation, and then in Leibniz notation, we end up with dy dx equals dy du times du dx. So this and this is what I would like you to have in your notes. This one you already have from the previous page. All right, let's go see how to use this. All right, an object moves along the x-axis so that its position at any time t greater than or equal to 0 is given by x of t equals cosine of t squared plus 1 find the velocity of the object as a function of t. So, how do I get from a position function to a velocity function? We take the derivative, so v of t is equal to x prime of t, and we have a composition, correct? Outside function is cosine, inside function is t squared plus 1. Notice I am not separating the t squared and the 1. Things that are added, subtracted, we'll just keep together. So now, using our method, we take the derivative of the outside, leaving the inside alone. Well, the derivative of cosine is negative sine. What do I have on the inside? Leaving the inside alone. T squared plus 1. Times the derivative of the inside. Now the 2t. Once again, unless you are asked to simplify, you don't have to, but we can just rearrange a little bit. Negative 2t sine of t squared plus 1.
What if they're asked to take the derivative again?
On this one, you would need product and chain.
That's
Okay?
up.
Can be. Let's go ahead, let's look. So what if we wanted the acceleration, which is the derivative of velocity, which is the second derivative of position. Okay? Well, now I have a product. I would call this one my first, and this one my second. And these can get ugly quickly. So let's go ahead. So we would need product rule here. And within the product rule, we would need chain. So first times derivative of the second. How do we write that? Negative 2t, that's first, times derivative of the second, chain rule,
Cosine t squared plus 1.
cosine, sorry, my pen is delayed, t squared plus 1, times 2t. So, first times derivative of the second, plus second, t squared plus 1, times negative 2. It's a great question. We'll certainly run into it with product and chain. So here, we need a chain. Okay? All right, questions on this one? I'll hold off a second. I see pens going. Let's try another one. All right, try that one, please. At your desk, give it a try, and then we'll go over it up here. Okay, so we have sine of x squared plus x. Who is willing, please? Tell me what we have. Becky? Go ahead.
Cosine of x squared plus x.
Cosine of x squared plus x. That's 2x plus 1. That's it. Derivative of the outside, leaving the inside alone, times the derivative of the inside. All right. Look at this one. They get a little longer. We had one like this in the table where we were working from outside to inside. Find the derivative of g of t equals tan of 5 minus sine of 2t. Okay, so outside is easy enough to spot. What is that? Tan. So the derivative of tan is secant squared, leave the inside alone. Okay, now our inside is here. Let's take the derivative of that. And what do we get? So the derivative of 5 will be 0. Derivative of negative sine of 2t, that's another composition. So we take the derivative of negative sine, which is negative cosine, leave the inside alone. Times what? The most inside. All right. So, anytime you have a trig function of anything other than just x, you need chain rule. So cosine of 3x, if y equals that, y prime would be what? Negative sine of 3x times 3. One of the most forgotten things throughout the entire year is that times 3. It looks like such an easy little derivative, but people forget that chain rule. So this applies also when we get into exponentials, if we have e to something other than just x, or if we have phi to something other than just x. Chain rule will apply. I won't put those on here yet because we haven't done those derivatives yet. Okay? All right, let's see what else we have.
Can we go back to just that?
I can. Down here?
Yeah.
Okay, let's move on to our next example. So, chain rule also allows us to get to derivatives of parametric equations. So let's look at this and let's remind ourselves that a set of parametric equations, because that's why I have to say that instead of parametrized, that sounds very strange. Anyway, a set of parametric equations. Remember, parametric equations take an equation, listen, that is in y in terms of x, and it breaks it into two equations that represent the motion in the x and the motion in the y. Okay, so when we have parametric equations, we have an x equation and a y equation in terms of some third variable, which is most often time, or t. Okay, so we are still interested quite often in getting the derivative of y with respect to x, even if we're given parametric equations. Okay, so we can use chain rule to help us get to our dy dx. If we think about the fact that we have an x of t equation and a y of t equation, if we take their derivative with the variable t, then we would have dx dt, and here we would have dy dt. And then we think, how can I play with these two to get dy dx? Well, we can see that the way they've written it here is dy dt would be equal to dy dx times dx dt, and once again our dx's would cancel. So that is the chain rule, but most often we are looking for dy dx. So to isolate dy dx, we would have dy dt over dx dt. So this is how we would find dy dx given a set of parametric equations. dy dx is equal to dy dt over dx dt. very easy to work with. You would just take the derivative of your x equation, the derivative of your y equation, the derivative of y, and the derivative of x. Okay, so that is finding dy dx parametrically. And now let's go do line. So, find the line tangent to the right-hand hyperbola branch defined parametrically by x equals secant t, y equals tan t, between negative pi halves and pi halves for t. At the point root 2, 1, where t equals pi fourths. So they have to give us this little bit of extra information because we have parametric equations, so they have to tell us the time that we're interested in. All right, well, the line tangent to the function, what am I going to look for in the end? Y minus blank equals blank times x minus blank. And what will I put in here? What? No? No?
Root 2.
Root 2. We put in the x. Remember, this is our x and this is our y. We are going to get x and y came from dealing with pi fourths, but still x and y are what go into the equation. So here we would put in root 2. And here I would put in what? 1. And what I need here, since I'm writing the equation of the line, tangent to the curve, I want dy dx, because this is equation y in terms of x. So I need to find dy dx. Well, we can use the chain rule that we just saw. We will take dy dt over dx dt. All right, well, x is secant t. What is dx dt? Very good. Secant t, tangent t. Okay, and what is dy dt? Sorry, let me get y down. Y is tan t. And dy dt? Okay. So that means dy dx will be what over what? I'm going to write it as secant t, just so we can see and I cancel easier, over secant t tangent t. We get our cancel here. And secant is 1 over what? Cosine. So secant is 1 over cosine.
1 over sine.
And tangent is sine over cosine. I'll write it out. You're all getting there anyway. 1 over cosine t times cosine t over sine t equals 1 over sine, which is cosecant t. All right. So what we need here is cosecant t when t equals what? Pi fourths.
So, you do it 1 over sine t, right?
You can do 1 over sine t.
So just look at the...
Oh, yes, so to figure it out, yes. Yep. So this is cosecant of pi fourths is 1 over sine of pi fourths. What is sine of pi fourths? Root 2 over 2. So what is cosecant? Sorry, let me get back here. 2 over root 2, and you can leave it just like that. Or you could simplify it to just root 2. Okay? So pretty easy to work with. You just need to remember, for dy dx, make sure you put dy dt on top, so that's a very common error as well. People know to do dy dt over dx dt, but they take the derivative, when they are doing their process, they take the derivative of x first and y second, and then they just put the x one on top and the y one on the bottom. So just be careful, dy dt over dx. Okay? Questions on that one? Do I need to scroll back down?
Yeah.
Yeah. Okay. Hand over. Oh, leave him alone. Leave him alone. And our final answer is here. I want a number. That's going to be my convention in this room. I want a number here. Because people keep giving me the function without plugging in anything. So just know that with the slope, I want a number. If possible, I want a number. All right. So your assignment sheet is up on the website, chapter 4, and it is up to date. Let me see if I have